Pluto does not orbit alone. It has a companion so large that Pluto itself is pulled around by it. That companion is Charon, a frozen moon more than half the diameter of Pluto, and unlike Earth and the Moon, the two worlds do not orbit around a point buried inside the larger body. Their shared gravitational center, called the barycenter, sits in empty space between them. In other words, Pluto and Charon behave less like a planet and its moon, and more like two worlds locked together. But their strange relationship is only the beginning. When New Horizons finally reached the Pluto system in 2015, scientists saw a moon that looked as though something had tried to tear it apart. Across Charon's surface runs an enormous system of fractures and canyons stretching for more than 1,000 miles. Some plunge several miles deep. They were not carved by rivers or weather, and there is no enormous impact scar capable of easily explaining them. Something happened inside the moon itself, and whatever happened was powerful enough to reshape a world hundreds of miles across. Then there is Charon's North Pole. Most of the moon is pale gray, covered in ancient water ice. But sitting across its northern region is a vast dark red stain, completely unlike the terrain surrounding it. Stranger still, understanding that stain may require looking not at Charon, but at Pluto thousands of miles away. For decades, astronomers expected Charon to be little more than another frozen relic at the edge of the solar system. One brief encounter revealed something very different: a fractured world, a mysterious red pole, evidence of enormous changes hidden beneath an exterior that now appears almost completely dead. And because New Horizons could not stop, humanity saw all of it during a single passage before the spacecraft disappeared deeper into the darkness. If space content like this is your thing, we've got plenty more. Subscribe, and you'll have a new documentary waiting for you next time you need one. Let's talk about what we actually know. For most of the 20th century, Charon was hiding inside Pluto's blur. No telescope had separated the two worlds clearly enough to reveal what was there. Then, in 1978, astronomer James Christie noticed something peculiar on photographic plates taken at the United States Naval Observatory. Pluto appeared slightly stretched, with a small bump along one side. Other plates showed the same distortion, but the bump changed position. It followed a repeating pattern around Pluto. Christie realized he was looking at another world. The discovery initially faced skepticism. A companion this substantial had escaped detection for decades, and the evidence came from tiny photographic irregularities. Yet continued observations confirmed the pattern. Pluto possessed a large companion, later named Charon. Even after its discovery, Charon remained almost entirely inaccessible to human eyes. Ground-based observatories could measure its motion, while the Hubble Space Telescope eventually separated Pluto and Charon into distinct points. Still, the moon itself remained only a handful of pixels. Scientists calculated its mass, size, and orbit with remarkable precision, while its landscape remained unseen. Its neighborhood made direct observation especially difficult. Pluto and Charon occupy the Kuiper Belt, a broad population of frozen bodies beyond Neptune. You can think of this region as the solar system's frozen outer archive. Material left from planetary formation has remained there for roughly 4.6 billion years, preserved under temperatures approaching absolute zero. Within this distant setting, Pluto and Charon perform an unusually precise gravitational dance. Charon completes one orbit every 6.387 Earth days. Pluto rotates once in exactly that same interval. Both worlds are mutually tidally locked. This means each continuously presents the same hemisphere toward the other. If we could stand on Charon's Pluto facing side, Pluto would remain fixed in one region of the sky. Neither world ever turns another face toward its companion. Distance also shaped everything humans could learn about them. Sunlight requires more than 5 hours to reach Pluto. During the New Horizons encounter, radio transmissions required about 4 hours and 25 minutes to cross the gulf between spacecraft and Earth. A command could not produce an immediate response. By the time information arrived, the event that produced it had happened hours earlier. That remoteness influenced scientific expectations. Before New Horizons, researchers generally pictured Charon as an ancient, heavily cratered sphere of water ice. Its small size and extreme cold seemed unfavorable for prolonged geological activity. Billions of years should have left it preserved like a fossil, recording impacts while producing little change of its own. Instead, the first detailed views exposed an unexpectedly complicated geological record. Vast fractures crossed the crust. Broad plains suggested resurfacing. Different terrains preserved evidence that Charon had once possessed enough internal energy to transform itself. The featureless ice ball had never existed. What remained was the harder problem, explaining how such a small world, so far from the sun, had acquired such an eventful geological history. On July 14th, 2015, there was no opportunity for correction. New Horizons was already racing through the Pluto system at roughly 32,500 miles per hour. At that speed, London and New York would be separated by less than 7 minutes of flight. The distance from Earth to our moon could disappear beneath the spacecraft in under 8 hours. Its trajectory allowed no second attempt. New Horizons carried insufficient fuel to break into orbit, and turning around was impossible. Months earlier, engineers had programmed the encounter sequence in precise detail. Cameras, spectrometers, and particle instruments would point toward predetermined targets at predetermined moments. From the Johns Hopkins University Applied Physics Laboratory, controllers watched those instructions unfold from roughly 2.8 billion miles away. They could observe the mission, but meaningful intervention was impossible. Even light needed several hours to cross the distance. By the time anyone on Earth learned that something had happened, New Horizons had already traveled far beyond it. During closest approach, the spacecraft concentrated on gathering data rather than transmitting it. The detailed pictures therefore arrived later, carried home through an extraordinarily narrow radio connection. Information crossed interplanetary space at roughly 1 to 2,000 bits per second, slower than many household internet connections from the 1990s. Then Charon began appearing in detail. Across much of the visible hemisphere stretched an immense system of fractures. Some formed broad troughs with towering walls, creating a tectonic belt that seemed to divide entire regions of the moon. These structures were far beyond the ordinary impact scars expected on an ancient frozen body. Their geometry suggested that large portions of the crust had moved. Farther south lay another surprise. A broad plain appeared remarkably smooth, carrying far fewer obvious impact craters than surrounding terrain. Craters accumulate with time, so their scarcity matters. Something had altered or covered an older surface after many earlier impacts had already occurred. The north presented a different puzzle. There, against Charon's predominantly gray terrain, appeared a broad reddish region concentrated around the pole. Its color demanded a chemical explanation, yet the obvious geological sources were missing. Scientists could see the feature clearly before they understood what material had produced it. No single download delivered the complete answer. New Horizons stored an enormous collection of observations, then transmitted them gradually across billions of miles. Returning the full encounter dataset required 16 months, continuing until late 2016. For more than a year, one day of exploration kept unfolding on Earth as researchers assembled those fragments. Their earlier picture of Charon became increasingly difficult to preserve. The surface contained evidence of resurfacing, unusual chemistry, and large scale tectonic deformation. Among those discoveries, the fractures carried the deepest geological record. A crater describes something that struck a world. A tectonic canyon can preserve forces generated beneath its crust. Charon's immense broken terrain therefore offered something more valuable than appearance alone, a physical record of processes that had once operated inside the moon itself. 4 billion years ago, the Pluto system may have looked nothing like the orderly arrangement we know today. The leading explanation for Charon begins with two substantial bodies occupying the same crowded region of the young Kuiper belt. One was Proto-Pluto. The other was another large icy world moving onto a collision course. Their encounter appears to have been oblique and relatively slow by planetary standards. A direct, high-speed impact could have shattered or vaporized enormous portions of both objects. Instead, computer simulations favor a glancing collision that stripped material from their outer layers while leaving much of Proto-Pluto intact. Water ice, silicate rock, and other debris spread into orbit. Gravity then began gathering those fragments together. Across thousands, perhaps millions of years, collisions among smaller pieces reduced their relative motions. Material accumulated into larger bodies until one dominant companion emerged, Charon. We have seen a related process closer to home. Roughly 4.5 billion years ago, a body called Theia probably struck the young Earth. Debris thrown into orbit, eventually assembled into our moon. Around Pluto, however, the resulting companion became proportionally enormous. Charon measures 51% of Pluto's diameter and contains roughly 12% of its mass. If our moon held the same proportions relative to Earth, its scale would approach that of Mars. Several clues support this impact origin. Charon's composition resembles material expected from Pluto's outer layers. Its orbit is also nearly circular and closely aligned with Pluto's equator. A randomly captured Kuiper belt object would more naturally retain an inclined or eccentric path unless later interactions dramatically altered it. Gravity continued reshaping the pair after Charon assembled. Tidal forces distorted both bodies slightly, converting rotational energy into heat and gradually slowing their spins. Eventually, each rotation synchronized with their shared orbital period of 6.38 and 7 Earth days. The configuration established during that early evolution remains today. Charon was probably not the collision's only surviving product. Styx, Nix, Kerberos, and Hydra likely assembled from the same debris field. These smaller moons now travel around the Pluto-Charon barycenter in near resonant orbital patterns, where their periods fall close to simple numerical relationships with Charon's orbit. Their dimensions range from only a few miles to several dozen miles. The collision also helps explain Charon's subdued chemistry. Volatile substances, materials that readily become gases at low temperatures, were depleted during its formation. Some remained preferentially with Pluto, while impact heating removed others from the debris. Charon therefore emerged richer in water, ice, and rock, with far less nitrogen and methane available at its surface. Yet the rock carried something important inside it. Locked within Charon's silicate interior were naturally radioactive elements. Their atomic decay would release heat gradually across immense spans of time, giving this newly assembled frozen world an internal energy source long after the violence of its birth had ended. Deep beneath Charon's frozen surface, time itself once produced heat. The source was embedded inside the rock, where unstable atoms had been present since the moon assembled from ancient planetary debris. Charon contains approximately 60% rock and 40% water ice by mass. Its bulk density revealed this mixture long before anyone could examine its geology closely. Neither ice nor rock alone can reproduce the measured density. Together, they describe a differentiated interior where denser, rocky material became concentrated toward the center. Within that rock are uranium 238, thorium 232, and potassium 40. These radioactive isotopes decay naturally, meaning their unstable atomic nuclei gradually transform into more stable forms. Each transformation releases a small amount of energy, accumulated across an entire rocky interior. Those tiny releases matter. Scientists call this radiogenic heating, the production of internal warmth through radioactive decay. Nothing explodes, no reactor is required. Individual atoms simply change over immense spans of time, releasing energy continuously into the material surrounding them. We live above the same process. Inside Earth, radioactive decay contributes substantially to the heat escaping from our planet today. Combined with energy retained from Earth's formation and other internal processes, that warmth helps sustain mantle convection and geological activity. Charon had fewer options. There was no nearby giant planet repeatedly flexing its interior through powerful tides. Its small size also allowed heat to escape more efficiently than it does from larger worlds. Yet early in Charon's history, radioactive elements were more abundant, and their combined energy output was greater. During roughly the first billion years, thermal models suggest that enough heat accumulated within Charon to melt water ice at depth. The surface remained intensely frozen. Far below, conditions could be different. Pressure increased with depth, while warmth rose from the rocky interior. Heat traveled outward primarily through conduction, the transfer of thermal energy directly through neighboring material. Ice conducted that energy toward the colder exterior, creating a steep thermal structure through the moon. Somewhere between those extremes, water could remain liquid. Picture the arrangement from the center outward. A rocky interior occupied the deepest region. Above it rested liquid water, enclosed beneath a thick shell of solid ice. Space surrounded everything beyond that crust. No sunlight penetrated to the water. Surface weather could never reach it. This basic architecture appears elsewhere across the outer solar system. Europa, Enceladus, Ganymede, and Titan all provide evidence for present or past internal oceans. Several benefit from tidal heating generated by gravitational interactions with giant planets. Charon developed under harsher circumstances. Atomic decay within its own rock supplied the crucial energy, allowing liquid water to persist where sunlight offered almost nothing. But radioactive elements do not release heat forever at the same rate. Their abundance declines as decay proceeds. Charon's internal furnace therefore weakened with age, leaving its buried water dependent on an energy source that was steadily fading. Beneath Charon's crust, liquid water occupied a place completely removed from the surface environment. Its upper boundary was solid ice. Beneath it lay rock. Between them stretched a pressurized ocean receiving its energy from below. Near the ice boundary, temperatures may have remained only slightly above 32 degrees Fahrenheit. Deeper water closer to the rocky interior could have been warmer. The precise temperature profile remains uncertain, but thermal models allow this buried reservoir to persist for hundreds of millions of years, perhaps approaching a billion. Depth brought another important condition: pressure. At the ocean floor, The weight of water and overlying ice may have produced pressures hundreds of times greater than Earth's atmosphere at sea level. Under such conditions, water interacts differently with minerals. Dissolved substances can remain stable, chemical reactions can change, and contact between warm rock and water can create complex mixtures. New Horizons found an important clue within Charon's surface ice: spectroscopic measurements, which identify materials through the wavelengths of light they absorb and reflect, detected ammonia compounds. Their presence matters because ammonia acts as an effective antifreeze when mixed with water. A sufficiently concentrated water and ammonia mixture can remain liquid near minus 143 degrees Fahrenheit. That dramatically extends the temperature range where an internal ocean could survive. Charon's buried sea may therefore have been a brine, meaning water containing dissolved substances rather than chemically pure water. That mixture could remain liquid as the moon gradually cooled. What would conditions have been like within it? Sunlight could never penetrate the ice shell. Photosynthesis was impossible. Any significant chemistry depended upon energy emerging from the rocky seafloor and reactions between water and minerals. Earth provides a useful comparison. Around deep ocean hydrothermal systems, seawater interacts with heated rock and acquires dissolved chemicals. Microorganisms can exploit the resulting chemical gradients without requiring sunlight. Charon may have possessed some broadly comparable ingredients, although we have no evidence that its seafloor ever developed vigorous hydrothermal circulation. That distinction matters. Liquid water alone does not establish habitability, and habitability does not establish biology. Heat, water, minerals, and chemical complexity merely create possibilities. We cannot determine from New Horizons observations whether those possibilities ever progressed further inside Charon. Time eventually changed the balance. Radioactive isotopes continued decaying toward more stable forms, reducing the heat supplied by the rocky interior. Energy escaped outward through the ice faster than the weakening interior could replace it. The ocean began losing its thermal support. Freezing followed gradually, advancing through a reservoir that may have endured across an enormous fraction of Charon's early history. As liquid water became solid ice, its physical volume increased by approximately 9%. Inside a confined moon, that additional volume had nowhere available to disappear. Rock bounded the ocean below, while a rigid shell enclosed it above. The pressure generated by freezing was therefore transferred directly into Charon's crust. Freezing water behaves strangely. Most liquids contract as they become solid, packing their molecules closer together. Water does the opposite. Its molecular structure opens into an ordered crystalline arrangement, making solid ice less dense than liquid water. That is why ice floats. It also means freezing water expands by approximately 9%. Inside Charon, that property operated on a planetary scale. As the buried ocean cooled, the freezing front advanced through the remaining liquid. Newly formed ice demanded additional volume, while the surrounding crust was already rigid. The outer shell had become thick, brittle, and mechanically resistant to deformation. Expansion from below steadily increased stress throughout it. Eventually, the crust exceeded its strength. Fractures opened along structural weaknesses and propagated across enormous distances. This process probably unfolded across tens of millions of years. Each additional volume of frozen ocean increased the strain, allowing existing fractures to widen while new ones spread through neighboring terrain. New Horizons photographed the surviving result as a vast tectonic belt of canyons, scarps, and troughs crossing much of Charon's visible hemisphere. Tectonics simply describes large-scale deformation of a world's crust. Here, the dominant style was extensional tectonics, where crust is stretched apart until blocks separate and the terrain between them drops. Serenity Chasma provides one of the clearest examples. The immense trough extends for more than 120 miles. In places, it spans roughly 25 to 30 miles across and descends between 3 and 4 miles below surrounding terrain. For comparison, Earth's Grand Canyon reaches roughly 277 miles in length, yet its greatest depth is around 1 mile. Serenity Chasma was produced through an entirely different mechanism. No river excavated it. The crust itself separated as Charon expanded from within. Nearby Manjet Chasma continues the same broad tectonic system, carrying the structural disruption farther across the surface. Together, these connected features reveal that the deformation was regional rather than confined to one isolated break. Farther north, Kalush Chasma extends roughly 250 miles and may reach around 8 miles deep. That places its greatest relief beyond the depth of Challenger Deep, Earth's deepest known ocean point, which descends almost 7 miles below sea level. Across the hemisphere, examined by New Horizons, the connected tectonic belt extends for at least 1,100 miles. On a world only about 750 miles across, that scale becomes difficult to treat as an ordinary surface feature. We are looking at deformation spanning a substantial fraction of the moon itself. The fractures also preserve direction. Their orientation, width, and displaced crustal blocks allow scientists to reconstruct how Charon's exterior responded to internal expansion. Each trough records stretching, each scarp marks displacement. Together, their geometry preserves the mechanical history of a buried ocean becoming ice, forcing the moon's rigid exterior outward until the crust could no longer remain intact. A fracture is more than damage. Its shape preserves the direction of the forces that produced it. On Charon, the Great Tectonic Belt carries this information across the landscape, allowing scientists to reconstruct movements that ended billions of years ago. Serenity Chasma displays extensional faulting, where sections of crust move away from one another. Pull-apart faulting occurs when two tectonic blocks separate and the ground between them drops, producing an elongated valley. The geometry differs fundamentally from compression, where crust is squeezed together and pushed upward. We see comparable structures on other worlds. Earth's East African rift developed as continental crust, stretched and separated. The Basin and Range province of the American West contains broad valleys created through extension. Mars preserves immense extensional structures within Valles Marineris. Relative to Charon's small diameter, however, its tectonic deformation occupies an extraordinary fraction of the entire world. The orientation of those fractures reveals something crucial. Charon's crust was stretching outward across its surface. This pattern fits an interior increasing in volume, forcing the exterior to accommodate expansion from beneath. Yet the tectonic belt also marks a striking geographical boundary. North of it lies Oz Terra, a rugged region dominated by ancient highlands, fractures, and heavily modified terrain. Southward spreads Vulcan Planitia, an expansive plain whose smoother surface contrasts sharply with the broken landscapes above it. The difference appears immediately in New Horizons imagery. Even Serenity Chasma extends beyond its obvious boundaries. Its northern wall continues for roughly 120 miles as a major scarp, essentially a long cliff created by displacement of the crust. Structural deformation, therefore, reaches farther than the canyon floor alone suggests. Vulcan Planitia creates another problem. Small bodies in the Kuiper Belt accumulate impact craters over immense spans of time. Without erosion or geological resurfacing, those scars remain. Yet portions of the southern plain contain fewer craters than the northern highland. Scientists use crater density, the number of impact craters within a given area, to compare the relative ages of planetary surfaces. More craters generally indicate longer exposure. By that measure, Vulcan Planitia appears younger than Oz Terra. Something modified the south after the older northern terrain had formed. The fractures provide a possible route. Deep breaks penetrating Charon's shell could have connected warmer material below with the surface. Water mixed with ammonia may have risen through these openings as mobile slush spread across low terrain and frozen again. That process is called cryovolcanism, meaning ice volcanism. Instead of molten rock erupting as lava, water-rich mixtures or other volatile materials reach the surface and solidify. Such flows could explain why older craters disappeared beneath younger material across Vulcan Planitia. Yet, interpreting ancient textures from one brief spacecraft encounter leaves substantial uncertainty. The cryovolcanic explanation remains scientifically debated because Charon's smooth southern plains preserve evidence of resurfacing without revealing every detail of how that resurfacing occurred. Across the southern half of the hemisphere, photographed by New Horizons, Charon seems to lose much of its ancient texture. The battered highlands give way to Vulcan Planitia, a broad plain where impact craters become noticeably less common. For planetary geologists, their absence is evidence in itself. Small worlds normally preserve impacts exceptionally well. Charon has no substantial atmosphere to weather its terrain, no rain to erode crater walls, and no exposed liquid capable of reshaping the landscape. Once a crater forms, some geological process must intervene if that crater later disappears. Vulcan Planitia contains signs that such intervention occurred. The leading explanation involves cryovolcanic resurfacing. During Charon's tectonic episode, deep fractures may have become conduits, pathways connecting pressurized material inside the moon with its exterior. Remaining water mixed with ammonia could then rise through those openings and spread across the southern terrain. Ammonia changes the physics considerably. Mixed into water, it lowers the freezing temperature, allowing mobile material to persist under conditions where pure water ice would already be solid. Instead of familiar molten lava, Charon may have released water-rich slush that moved across the landscape before freezing into new crust. The resulting flows could bury older terrain. Existing craters would vanish beneath successive deposits, while smaller irregularities became softened or covered. Once frozen, the resurfaced plain would begin accumulating new impact scars, creating the younger crater population we observe today. New Horizons images provide additional clues. Parts of Vulcan Planitia display irregular textures and broad surfaces compatible with material that once moved before becoming rigid. The terrain lacks some of the sharp, densely cratered appearance expected from a surface left untouched since Charon's earliest history. Similar geological ideas appear elsewhere. Triton, Neptune's largest moon, possesses broad young plains, often interpreted through cryovolcanic processes. Titan also shows features that may involve icy eruptions. Pluto contains regions where volatile ices have flowed and resurfaced terrain, demonstrating how unfamiliar materials can behave geologically at extremely low temperatures. Charon's evidence remains less complete. We cannot determine precisely how thick the proposed deposits became. Their total duration is uncertain as well. Some models place the main resurfacing episode deep in Charon's early history, while available observations cannot establish whether smaller episodes continued substantially later. One structural detail strengthens the connection with tectonics. Vulcan Planitia does not blend gradually into the rugged northern terrain. Its boundary follows the Great Fracture System with remarkable sharpness. That geometry suggests the same crustal architecture that opened Charon may also have controlled where interior material could reach the surface. So the southern hemisphere records a landscape repeatedly altered from below, then preserved after activity faded. Yet elsewhere on Charon, alteration followed a completely different route. At the North Pole, the surface acquired material, whose origin lay beyond the Moon itself, carried across space from Pluto through a process governed by atmospheric escape and chemistry. Color makes Charon's North Pole immediately recognizable. Against the Moon's gray and whitish terrain lies a broad reddish-brown region known as Neverland Regio and informally called Mordor Macula during the New Horizons mission. Its tones resemble rust and weathered wood, spreading across the pole in a diffuse stain unlike surrounding ice. The color comes from material called tholins. These are complex, reddish organic residues produced when simple carbon-bearing molecules undergo prolonged bombardment by ultraviolet radiation or energetic charged particles. Tholins are not one specific chemical substance. They are complicated mixtures created through chains of radiation-driven reactions. We find similar chemistry throughout the outer solar system. Tholins contribute to Pluto's reddish terrain and Titan's orange atmospheric haze. They also appear across numerous distant icy bodies exposed to radiation for immense spans of time. Charon presents a chemical problem, however. Its surface contains abundant water ice, while methane and nitrogen are scarce. The raw ingredients needed to produce the polar material cannot easily be supplied by Charon itself. Pluto provides them. Methane from Pluto's tenuous atmosphere can acquire enough energy to escape its weak gravitational hold. Pluto's surface gravity is only about 6.3% of Earth's. In its upper atmosphere, energetic molecules can therefore reach escape velocity and enter surrounding space. Scientists call this atmospheric escape, the gradual loss of atmospheric particles from a world into space. New Horizons measured escaping material around Pluto, confirming that its atmosphere extends outward and loses particles. Some methane leaves the Pluto system entirely. Another fraction can encounter Charon, whose surface lies only about 12,200 miles from Pluto's center. Once methane reaches Charon, the poles provide an effective trap. During the long polar winter, temperatures can fall below minus 380 degrees Fahrenheit. Charon experiences extreme seasons because the Pluto system takes roughly 248 Earth years to complete one orbit around the Sunday. A pole can therefore remain without direct sunlight for more than a century. At those temperatures, arriving methane can freeze onto the surface. This process is called cold trapping. A volatile molecule lands on terrain cold enough to prevent immediate sublimation, the direct transition from solid back into gas. The molecule remains available for later radiation chemistry. The effect accumulates slowly. Pluto continuously loses traces of atmosphere. Some fraction reaches Charon, and the polar environment captures part of that material. Radiation then alters what remains on the surface, producing increasingly complex organic residues. Seen this way, the reddish pole records an exchange between two separate worlds. Charon does not need its own methane rich atmosphere to acquire the chemistry visible there. Its companion supplies the ingredients across open space. For billions of years, Pluto has effectively painted Charon molecule by molecule, leaving a continental scale polar stain whose material began its journey on another world. A single methane molecule arriving from Pluto begins a transformation that may outlast mountains. Methane is the simplest hydrocarbon, built from one carbon atom bonded to four hydrogen atoms. At Charon's winter pole, these wandering molecules settle onto intensely cold ice and remain frozen there. Their chemistry changes under radiation. Even across more than 3 billion miles from the sun, ultraviolet radiation still carries enough energy to alter exposed molecules. Charged particles carried through the solar wind provide another source. Together, these energies repeatedly strike the deposited methane. Individual molecular bonds begin breaking. Carbon separates from hydrogen, fragments collide, and new bonds form. Continued irradiation produces simple hydrocarbons first. More complicated structures follow, including interconnected carbon rings and long molecular chains. The chemistry keeps building. Over immense periods, this processing creates tholins, the heavy reddish brown organic residues covering Charon's northern polar terrain. Their molecular structures interact with visible light differently from the original methane. Networks of connected carbon bonds preferentially absorb shorter blue and green wavelengths while reflecting more reddish and brown light. You can think of the color as chemistry made visible. Every darker patch records countless molecular rearrangements driven by radiation across geological time. Charon's extraordinary seasons regulate how that chemistry develops. One journey around the sun requires roughly 248 Earth years. Each pole, therefore, experiences extraordinarily prolonged periods of sunlight and darkness, with seasonal conditions persisting for more than a century. During polar summer, sunlight warms the surface enough for some lighter volatile compounds to sublimate. Sublimation occurs when frozen material passes directly into gas. These molecules can migrate elsewhere or escape Charon entirely. The heavier tholin residues remain behind. When winter returns, temperatures fall again and fresh methane arriving from Pluto becomes trapped. Another chemical layer can begin. Irradiation transforms that material. Summer removes some volatile remnants, and the more stable organic residue survives. Repeated across roughly 4 billion years, the process could have operated through about 16 million journeys of the Pluto system around the Sunday. How deep has that residue become? New horizons could determine its composition and distribution, yet it could not directly measure the deposit's full thickness. Models allow considerable uncertainty, with estimates ranging from inches to several feet in parts of the polar region. There is another missing piece. Charon's southern pole should experience the same alternating conditions over each orbit, creating a comparable opportunity for methane trapping and radiation chemistry. Yet New Horizons did not obtain similarly detailed views of that distant pole during its brief encounter. What we can see already changes the meaning of Charon's reddish stain. It demonstrates that neighboring worlds can exchange matter across thousands of miles, allowing one body's escaping atmosphere to become another body's surface chemistry. Charon carries Pluto's chemical signature directly upon its ice, preserved through millions of seasons of molecular exchange. Gravity gives every partnership a hidden center. For Earth and the Moon, that shared point, called the barycenter, lies inside Earth, roughly 2,900 miles from our planet's center. Both bodies orbit it, though the arrangement makes the Moon appear to circle Earth alone. Pluto and Charon behave differently. Their barycenter lies roughly 600 miles above Pluto's surface, suspended in open space between the two worlds. Pluto therefore travels around that point alongside Charon, tracing its own small circle rather than occupying the system's fixed center. That motion once betrayed Charon's presence. In 1978, James Christie noticed Pluto's photographic image developing a recurring bulge. The apparent distortion changed position predictably. A companion was pulling Pluto around their shared gravitational center. Their separation is only about 12,200 miles from center to center. Earth and the Moon, by comparison, are roughly 239,000 miles apart. Charon circles its barycenter at around 470 miles per hour, modest by spacecraft standards, yet sufficient to maintain this compact partnership. Mutual tidal locking makes the geometry stranger. Charon always presents the same hemisphere toward Pluto, while Pluto always presents the same hemisphere toward Charon. If you stood on Charon's Pluto-facing side, Pluto would occupy one permanent location overhead. It would never rise or set. Its apparent diameter would span roughly 7.6 times the width of our moon, as seen from Earth. At that scale, major contrasts across Pluto's surface would be visible without optical aid, including the bright heart-shaped region called Tomball Regio. Travel to Charon's opposite hemisphere, however, and Pluto never enters your sky. The same rule applies on Pluto. Across the hemisphere, facing away from Charon, the companion remains permanently beneath the horizon. This configuration is extraordinarily durable. No nearby giant planet supplies powerful external tides capable of dismantling the pair. Their locked orbital relationship should therefore persist on astronomical timescales, lasting until changes in the distant future of the solar system alter the environment around them. Four smaller moons share this gravitational architecture. Styx, Nix, Kerberos, and Hydra orbit the common barycenter in near-resonant patterns. Their orbital periods lie close to ratios of 3 to 1, 4 to 1, 5 to 1, and 6 to 1 relative to Charon. Because Pluto and Charon create a shifting gravitational field, these tiny moons can tumble chaotically instead of maintaining simple, orderly rotations. So the system we see is more than a planet with satellites. It is a binary pair surrounded by four smaller companions, linked through gravity, resonances, and chemical exchange. New Horizons exposed this architecture during one brief encounter after traveling 9.5 years. The spacecraft weighed roughly as much as a motorcycle and drew electrical power from radioactive plutonium, an element whose name itself came from Pluto. For most of its journey, New Horizons was barely awake. The spacecraft crossed billions of miles, with major systems powered down, conserving hardware, while a weekly radio tone told controllers on Earth that the machine remained healthy. Its journey had begun at extraordinary speed. Launched in January 2006, New Horizons departed Earth at roughly 36,400 miles per hour, the fastest launch speed ever achieved by a spacecraft leaving Earth. Yet Pluto remained years away. Jupiter changed the timetable. In February 2007, the spacecraft swept past the giant planet and performed a gravity assist. Jupiter's motion and gravitational field transferred orbital energy to New Horizons, increasing its outward speed by roughly 9,000 miles per hour. The maneuver shortened the voyage to Pluto by about 3 years. All of this was accomplished by a spacecraft weighing roughly 1,050 pounds, comparable to a large motorcycle. Electrical power came from a radioisotope thermoelectric generator, which converted heat from decaying plutonium 238 into electricity. Around the Pluto encounter, only about 200 watts were available. 7 scientific instruments shared that limited supply. The Long Range Reconnaissance Imager provided detailed telescopic photographs. Ralph mapped surfaces in visible and infrared wavelengths. Alice examined ultraviolet light for atmospheric studies. The radio science experiment investigated atmospheric and surface properties through radio signals. Solar wind around Pluto measured charged particles flowing from the Sun, while the Pluto Energetic Particle Spectrometer Science Investigation examined higher energy particles. A student dust counter recorded microscopic debris encountered during flight. On July 14, 2015, New Horizons passed about 17,900 miles from Charon. The long-range reconnaissance imager could distinguish features roughly 3,000 feet across in its sharpest global observations. What had once occupied only a few pixels became cliffs, plains, craters, fractures, and mountains. The spacecraft continued onward. On January 1, 2019, it encountered Arrokoth, a contact binary whose 2 lobes joined gently during the early solar system. At roughly 4 billion miles from the Sun during the encounter, Arrokoth became the most distant object ever explored closely by a spacecraft. Reaching these worlds required decades of persistence. Principal investigator Alan Stern spent years advocating for a Pluto mission through proposals, cancellations, redesigns, and renewed approval. New Horizons finally launched in 2006. Months later, Pluto was reclassified as a dwarf planet. The spacecraft kept traveling. A scientific label changed. The world awaiting exploration did not. Now we can measure the human scale against the distance. Thousands of people designed, assembled, tested, launched, navigated, and operated a machine weighing little more than a motorcycle. It crossed billions of miles for one brief passage through the Pluto system. Every photograph, spectrum, dust impact, and particle measurement then returned through a radio transmitter operating with only a few watts of power, carrying an unseen world home across deep space. Charon's interior no longer needs to move for its history to remain visible. After its ancient ocean froze, the moon settled into a differentiated structure, meaning materials of different densities became arranged into distinct internal layers. We cannot see those layers directly. Their existence is inferred from Charon's mass, radius, density, surface composition, and geological features. Deepest inside lies a rocky core rich in silicate minerals and other dense compounds. Models differ on its exact dimensions because no spacecraft has measured Charon's gravity field closely enough to map the interior. Even so, its bulk density indicates that rock makes up a substantial fraction of the moon, surrounded by a thick mantle of water ice. Above that core, water now exists as solid ice. The boundary that once separated an outer frozen shell from deeper liquid gradually disappeared as freezing progressed. Eventually, the former ocean became part of one continuous, solid interior. Only the uppermost material is directly observable. Charon's surface consists mainly of crystalline water ice, accompanied by trace ammonia-bearing compounds and darker organic material concentrated around the poles. Across that crust remain the fractures, plains, scarps, and impact structures produced during very different stages of its evolution. Today, surface temperatures can fall near minus 370 degrees Fahrenheit, depending on location and season. Under such conditions, familiar atmospheric gases such as nitrogen and oxygen would freeze onto the ground if sufficient amounts were present. Far below, radioactive decay still produces some heat, yet the remaining energy is vastly weaker than during Charon's youth. Long-lived radioactive elements continue decaying within the rocky material, but their present output appears insufficient to recreate the extensive melting required for another global subsurface ocean. The consequences are visible everywhere. Large-scale cryovolcanism appears to have ended billions of years ago. The forces responsible for opening enormous tectonic fractures have faded as well. Without substantial internal melting, convection, or strong tidal flexing, Charon lacks the mechanisms that continually reshape more active worlds. Could tiny internal adjustments still occur? They cannot be ruled out. No seismometer has ever operated there, so scientists cannot directly measure moonquakes or subtle movements beneath the crust. What the surface reveals, however, is a world whose major geological activity belongs overwhelmingly to its distant past. That makes preservation unusually important. Earth continually destroys portions of its geological record through erosion, plate tectonics, volcanism, oceans, and weather. Charon has none of those powerful recycling systems operating today. Its surface changes mainly through impacts, radiation processing, seasonal volatile chemistry, and extremely gradual space weathering. So when we examine Charon, we are reading material that has survived across immense stretches of time. Ancient fractures still preserve the response of its expanding interior. Resurfaced plains retain evidence of vanished internal liquids. The polar deposits continue recording material exchanged with Pluto. Charon has become a museum of its own evolution, with much of its geological record preserved for billions of years. Liquid water has never belonged exclusively to warm worlds. Across the outer solar system, several frozen moons conceal, or once concealed, enormous reservoirs beneath their crusts. Charon belongs among them in the past tense. Its ocean appears to have vanished, while other worlds still carry theirs today. Europa, orbiting Jupiter, is about 1,940 miles across. Evidence from spacecraft observations and magnetic measurements indicates a global salty ocean beneath an ice shell, perhaps several to a few dozen miles thick. Jupiter's gravity repeatedly flexes Europa through tidal heating, generating internal warmth. Estimates suggest its ocean could reach roughly 60 miles deep and contain more water than Earth's oceans combined. Farther outward, Saturn's moon Enceladus offers direct access to its interior. Barely 313 miles wide, it sprays water vapor, ice grains, salts, and organic compounds through fractures near its south pole. The Cassini spacecraft detected molecular hydrogen within those plumes. That hydrogen provides evidence for chemical reactions between warm water and rock on the seafloor, resembling processes associated with hydrothermal systems on Earth. Ganymede presents an even larger reservoir. At roughly 3,270 miles across, Jupiter's largest moon exceeds Mercury in diameter. Magnetic observations support a deep internal ocean, possibly arranged among layers of high-pressure ice. Ganymede also generates its own magnetic field, unique among known moons. Titan adds another variation. Saturn's largest moon spans about 3,200 miles and probably hides a water ocean beneath its icy exterior. Yet its surface also carries lakes, seas, rain, and river channels made from liquid methane and ethane. Water below, hydrocarbons above. Two very different liquid environments occupy one world. Against these active or potentially active oceans, Charon represents another stage of evolution. Its internal sea survived only while radioactive decay supplied enough warmth. Once that energy declined, freezing became irreversible. The resulting expansion fractured the crust, leaving structural evidence where liquid water itself can no longer be sampled. This changes how we think about habitability. Liquid water does not require a planet positioned at Earth's distance from the Sunday. Tidal flexing, radioactive decay, pressure, and antifreeze compounds can maintain it beneath surfaces, receiving very little sunlight. Charon pushes that principle toward smaller, colder bodies. More than 3 billion miles from the Sun, without sustained tidal heating from a giant planet, its rocky interior may still have supported liquid water for hundreds of millions of years. How many similar histories remain unread? The Kuiper Belt contains vast numbers of icy bodies, although only a small fraction approach Charon's size. Some may once have generated enough internal heat for buried oceans of their own. If so, extinct ocean worlds may be scattered throughout the solar system's distant frontier. Charon would represent a broader planetary pathway where water briefly becomes liquid beneath ice before freezing into geological memory. Across the galaxy, wherever rock, ice, and internal heat gather together, the conditions for hidden water may be far more common than sunlight alone would suggest. Could life ever have existed beneath Charon's ice? Scientifically, the answer must remain possible, but entirely unproven. Every organism we know depends on three broad ingredients: liquid water, usable chemical energy, and molecules capable of supporting complex chemistry. Ancient Charon possessed water. It also contained carbon-bearing material somewhere within its system. Energy remains the uncertain piece. On Earth, some ecosystems demonstrate how life can survive without sunlight. Around hydrothermal vents, seawater circulates through heated rock beneath the ocean floor. Chemical reactions release compounds that microorganisms can exploit for energy. Entire food webs develop around this process, supported by chemistry rather than photosynthesis. Charon offered a partially similar environment. Radioactive elements warmed its rocky interior for hundreds of millions of years, providing enough energy to maintain buried liquid water. Yet, warmth alone does not guarantee useful chemistry. Scientists do not know whether water circulated through fractures in Charon's core, reacted extensively with minerals, and returned carrying energy-rich compounds. The temperatures may have remained too low. Hydrothermal circulation could have been weak, intermittent, or absent altogether. Without sustained chemical gradients, an ocean can remain liquid while offering very little energy for emerging biology. Time presents another uncertainty. Earth's earliest evidence for life appeared relatively early in planetary history, although exactly how quickly life originated remains unresolved. Charon's ocean may also have survived for hundreds of millions of years, perhaps longer, but its environment was colder and probably less chemically energetic. Complex organic compounds do exist on Charon today. The reddish tholins concentrated near its pole demonstrate that elaborate carbon chemistry occurs within the Pluto system. Those compounds formed mainly through radiation, acting on material deposited at the surface. However, their presence does not show that comparable organic chemistry occurred within the ancient ocean. So we should keep the conclusion narrow. Charon may once have satisfied several basic requirements associated with habitability. No observation provides direct or indirect evidence that organisms ever appeared there. Even if primitive biology developed, the ocean eventually froze, internal circulation faded, and pathways capable of transporting biological signatures toward the surface disappeared. For astrobiology, Charon itself is therefore a difficult target. Its greater importance comes from what its history implies statistically. The Kuiper Belt may contain enormous numbers of substantial icy bodies. If some shared Charon's mixture of rock, ice, radioactive elements, and antifreeze compounds, temporary buried oceans may once have existed throughout this distant population. Beyond our solar system, similar bodies should accompany other planetary systems. Some may receive almost no meaningful stellar warmth while maintaining liquid interiors through their own geology. That possibility enlarges our definition of an ocean world. A galaxy containing countless frozen objects may also contain countless extinct seas, each surviving for a geological interval before its internal heat diminished. Charon becomes one historical data point within that larger population, showing us that liquid water can emerge in places once considered far too small, distant, and cold to possess it. Charon's neighborhood begins far beyond the familiar architecture of the planets. The Kuiper Belt stretches roughly from 30 to 50 astronomical units from the Sun, where one astronomical unit represents Earth's average orbital distance. Its outer region lies around 4,600,000,000 miles from the Sunday. Across that enormous zone, ancient objects circle in deep cold. Hundreds of thousands may exceed 60 miles in diameter. Trillions of smaller bodies could accompany them. Together they form a broad population of icy remnants preserved from the solar system's formation around 4,600,000,000 years ago. That age gives these objects unusual scientific value. Many contain primitive mixtures of water, ice, rock, and volatile compounds inherited from the disk that surrounded the young Sunday. Extremely low temperatures can preserve materials that disappeared or transformed elsewhere. When we examine them, we investigate some of the earliest surviving ingredients of planetary construction. Pluto ranks among the largest known members, although it is hardly alone. Eris, discovered in 2005, has a diameter comparable to Pluto's and helped ignite the classification debate, preceding Pluto's reclassification in 2006. Makemake, Haumea, Quaoar, and distant Sedna reveal further variety. Haumea even possesses a ring. Companions are common as well. Surveys indicate that a substantial fraction of Kuiper Belt objects belong to binary or multiple systems. Their existence suggests that pairing bodies was a natural consequence of the outer solar system's early evolution. Yet those partnerships did not necessarily form through the same mechanism. Arakoth demonstrated another possibility when New Horizons visited it on January 1st, 2019. Its two flattened lobes appear to have approached gently before joining into a contact binary, meaning two bodies physically touching as one object. Their collision probably occurred at only walking speed. Look across the wider population, and uniformity disappears. Some surfaces reflect considerable sunlight, others are darkened and reddened by complex organic residues. Certain objects possess moons or rings, while others remain solitary. Evidence of geological modification appears on some worlds, while many smaller bodies preserve far older terrain. That diversity gives Charon a broader significance. Its impact origin, vanished interior water, fractured crust, resurfaced plains, and interaction with Pluto may represent processes that occurred elsewhere among substantial Kuiper Belt bodies. We currently lack close observations needed to know how frequently. New Horizons remains the only spacecraft to examine Kuiper Belt objects at close range. Pluto, Charon, and Arakoth therefore carry an extraordinary scientific burden. From a few encounters, we are trying to reconstruct the history of an immense population spread across billions of miles. For you and me, that scale changes what Charon represents. It is one examined member of an ancient frontier containing countless unvisited worlds. A single day near Pluto transformed our understanding of that neighborhood, while almost everything surrounding it remains known only as distant points of light. Every detailed map of Charon contains an invisible boundary. Beyond it lies terrain, structure, chemistry, and history that no instrument has measured closely. New Horizons transformed our knowledge in 2015, yet the unanswered questions still outnumber the secure conclusions. Science often advances this way. Better observations enlarge the frontier of uncertainty. Most striking is Charon's unseen hemisphere. New Horizons observed one side with its highest resolution instruments during a fast flyby. Large portions of the opposite side remain poorly known. We cannot map the full continuation of the Great Tectonic Belt or determine whether southern landscapes mirror northern structures. The South Pole presents another mystery. If Pluto supplies material that creates the northern polar deposit, similar seasonal chemistry should operate in the south, yet its detailed appearance remains unknown. A comparable reddish deposit may exist there, but current observations cannot establish its form or extent. Even Charon's interior remains reconstructed rather than directly observed. Scientists infer layers from density, composition, tectonic patterns, and thermal models. No seismometer has listened for moonquakes. No radar has sounded through the crust. No instrument has measured heat flowing from Charon's interior. The model of rock, ice, and a former ocean fits the evidence, but we have never looked beneath the surface. Time is equally difficult to recover. Crater counting shows that Vulcan Planitia is younger than Oz Terra because fewer impacts remain visible there. That provides relative chronology, not a precise calendar. Without laboratory analysis of returned samples, major geological episodes may remain uncertain by hundreds of millions of years. The ancient ocean carries similar uncertainty. Did liquid water survive for roughly 500 million years? Nearly a billion? Or some interval between? That difference matters when considering chemical evolution, circulation, and the duration of potentially habitable conditions. Cryovolcanism raises another unresolved issue. No active eruption was detected during the encounter, yet one brief observation cannot prove that activity has permanently ended. Extremely cold worlds can operate on geological timescales far longer than human observation. At the North Pole, even the depth of the reddish organic material remains uncertain. Models permit deposits ranging from inches to several feet. Determining that thickness would reveal how efficiently Pluto has supplied material across billions of years. Ammonia adds another incomplete chapter. Scientists still debate how much was incorporated during Charon's formation, altered by radiation, transported through ancient geological activity, or gradually lost to space. Even the small moons remain unfinished portraits. Styx and Kerberos were photographed with limited resolution, leaving their shapes and surface properties imperfectly constrained. Consider what all this rests upon. The most detailed observations of Charon came from roughly one day of encounter operations. Those measurements then crossed billions of miles through an extraordinarily weak radio link, requiring about 16 months for the full Pluto system dataset to reach Earth. We possess one extraordinary close encounter with Charon. Around that narrow island of measurement stretches something much larger. Everything we have never seen, sampled, touched, or directly measured. Returning to Charon is less a question of scientific interest than of momentum. Researchers have discussed Pluto system orbiters since before New Horizons completed its encounter. A flyby can transform knowledge in hours. An orbiter could remain for years, mapping unseen terrain, watching seasonal changes, and measuring the system repeatedly from different angles. The difficulty begins at arrival. New horizons cross the Pluto system rapidly because it never needed to stop. An orbiter must shed enormous velocity after traveling billions of miles. Carrying enough chemical propellant for that braking maneuver increases spacecraft mass, which demands still more launch energy and fuel. With conventional chemical propulsion, studies commonly produce journeys lasting roughly 25 to 35 years when enough propellant must remain for orbital insertion. A spacecraft launched during this decade could therefore reach Pluto sometime in the 2050s or 2060s, depending on trajectory and planetary gravity assists. More advanced propulsion could change that arithmetic. Nuclear thermal propulsion uses a reactor to heat propellant before expelling it at high velocity, providing greater efficiency than conventional chemical engines. Ground programs have tested elements of the technology, but no nuclear thermal rocket has yet operated during a spaceflight mission. Designing an expensive Pluto mission around an unflown propulsion system adds another layer of risk. Scientific priorities matter just as much. The Planetary Science Decadal Survey, covering 2023 through 2032, recommended the Uranus orbiter and probe as the highest priority new flagship mission. Pluto and Charon remain scientifically compelling, yet they must compete with major investigations across Mars, Europa, Uranus, and other destinations. Mission studies have imagined several approaches. A Pluto orbiter could investigate atmospheric evolution while repeatedly mapping Charon. More specialized concepts could concentrate on Charon's geology and internal structure. A lander would offer measurements impossible from orbit, but landing safely after such an enormous journey would demand even greater mass, complexity, and cost. Remote astronomy continues, meanwhile. The James Webb Space Telescope can analyze infrared signatures from Pluto and Charon, helping scientists study surface composition. At that distance, however, it cannot produce detailed geological maps comparable with spacecraft images. Occultations provide another narrow window. When Pluto passes before a distant star, changes in the starlight reveal properties of its atmosphere. Astronomers have used such events to monitor Pluto since 1988. They are powerful measurements, yet they cannot replace another close encounter. Then comes the budget. Flagship planetary missions can cost several $billions and consume decades from early studies through arrival. Only a small number can be pursued at once. Outer solar system exploration therefore rewards patience on a generational scale. The people who eventually see Charon's southern hemisphere may already be alive. Some may be children today. The spacecraft that could show it to them has not yet been approved, and its long voyage has not begun. 4 billion years does not fit comfortably inside human intuition. We can write the number, compare it, divide it into eras. Yet Charon has existed across a span so immense that nearly everything familiar belongs only to its latest fraction. Some of Earth's oldest known rocks formed about 4 billion years ago. The Acasta gneiss of northern Canada contains rock roughly 4.03 billion years old. When those ancient minerals were forming, Earth remained a young planet, still carrying the consequences of violent impacts and intense internal heat. Charon already belonged to that early solar system. Life followed much later. Evidence suggests single-celled organisms existed on Earth at least 3.5 billion years ago, with some proposed traces extending toward 3.8 billion. Depending on how Charon cooled, its buried ocean may already have been shrinking or freezing while Earth's earliest biology was emerging. Then, enormous stretches passed. Complex multicellular organisms became widespread roughly 600 million years ago. By then, Charon's great geological transformations were probably ancient history. Its fractured crust had already recorded the expansion of freezing water. Cryovolcanic material had settled across southern plains. At the poles, radiation chemistry continued adding organic residue molecule by molecule. Animals established themselves on land roughly 400 million years ago. Earth's continents repeatedly joined, separated, collided, and rearranged. Charon continued circling Pluto, preserving terrain already unimaginably old. Our own species appeared only about 300,000 years ago. That represents roughly 0.0075% of Charon's 4 billion year existence. Written as a percentage, the interval seems almost absurdly small. Every human civilization occupies a still thinner slice. Across Charon's lifetime, Earth has experienced 5 major mass extinction events. Continents have assembled into supercontinents and broken apart again. Biological evolution transformed microscopic organisms into forests, insects, dinosaurs, whales, birds, and humans. Meanwhile, the sun itself has gradually brightened since its youth, increasing its luminosity by roughly 30%. Against those changes, Charon preserves another kind of chronology. Its major canyons were already carved before animals walked across terrestrial landscapes. The broad plains had frozen long before any human ancestor existed. Seasonal cycles continued around Pluto, each orbit lasting 248 Earth years. Micrometeorites arrived occasionally. Polar chemistry accumulated slowly. You could place the entire recorded history of civilization near the very end of that timeline and barely mark it. Even the future becomes strange at this scale. Barring some unexpected disruption, Charon's ancient fractures can remain recognizable for billions of additional years. The sun will continue evolving. Earth will change beyond recognition. Pluto and Charon will continue their paired orbit, 4 billion years behind them, billions more ahead, and our first close view lasted a single day. The future of Charon is tied to a star nearly 4.5 billion miles away. The Sun is about 4.6 billion years old, roughly halfway through its hydrogen-burning main sequence lifetime. Since its formation, its luminosity has increased by about 30%. That gradual brightening will continue. Over the next billion years, additional sunlight will alter Pluto's volatile surface. Nitrogen, methane, and carbon monoxide ices respond readily to temperature, shifting between solid and gas as Pluto travels around the Sunday. Greater solar output should intensify these cycles and promote long-term volatile loss to space. Pluto's atmosphere will evolve with them. As that reservoir changes, Charon changes too. Methane escaping Pluto currently supplies raw material that can reach Charon and contribute to polar chemistry. If Pluto eventually loses much of its accessible methane, that transfer weakens. The reddish organic deposits at Charon's poles would then accumulate more slowly, perhaps eventually stopping altogether. Their final thickness would preserve the duration of an exchange spanning immense time. The larger transformation comes roughly 5 billion years from now. After exhausting hydrogen in its core, the Sun will leave the main sequence and eventually swell into a red giant. Its outer layers will expand enormously, threatening Mercury and Venus and potentially reaching Earth's present orbit. Pluto and Charon are far beyond that expansion. Distance will spare them from direct engulfment. But the red giant sun will become thousands of times more luminous than it is today, sending vastly more energy into the outer solar system. For Pluto and Charon, familiar surface conditions would disappear. Ices stable under today's weak sunlight would warm and vaporize. Nitrogen, methane, carbon monoxide, and exposed water ice could be redistributed or lost as the surfaces undergo chemical and physical changes. Processes that presently require centuries could accelerate under an environment unlike anything these worlds have experienced. Then the sun itself will shed its outer layers. Expelled gas will briefly surround the exposed stellar core before dispersing into interstellar space. What remains will be a white dwarf, an Earth sized stellar remnant with enormous density and no sustained nuclear fusion. Its light will fade over billions of years. Far away, Pluto and Charon would cool again. Their surviving volatile material would freeze onto surfaces receiving progressively less stellar energy. The pair's mutual gravitational lock should persist unless an external encounter disrupts the system. They would continue circling their common center while orbiting the fading remnant of the Sunday. And Charon's oldest structures could outlast nearly everything that once surrounded them. Canyons created billions of years before our arrival may remain recognizable after the sun has abandoned its present form. Their walls and geometry would circle a white dwarf beneath a far dimmer sky, preserving the physical record of an ocean gone for ages, inside a planetary system transformed beyond recognition. Before planets settled into familiar paths, the young solar system was crowded. Rocky and icy bodies crossed unstable orbits, striking one another as planets accumulated mass. Collisions were part of planetary construction. Pluto and Charon preserve one outcome from that formative era. Their defining impact probably occurred within the solar system's earliest hundreds of millions of years. The protoplanetary disk, the broad reservoir of material from which planets formed, still contained numerous substantial bodies. Encounters could merge them, shatter them, or leave survivors gravitationally bound. Pluto and Charon emerged from this environment as an unusually stable pair. Another period of upheaval may have followed much later. The Nice model, named after the French city where researchers developed it, proposes that the giant planets migrated substantially after formation. Their changing gravitational relationships scattered smaller objects throughout the outer solar system. Some were thrown inward, others moved outward or escaped entirely. One version of this history connects giant planet migration with intense impacts recorded across ancient surfaces. The exact timing and magnitude of the proposed late heavy bombardment remain debated, and modern research suggests the bombardment history was more complicated than one brief spike. Still, planetary migration almost certainly reshaped the distribution of early small bodies. Pluto and Charon survived that changing architecture. Their own formative collision came earlier, when planet building remained active. That distinction matters. Charon carries evidence from an epoch that Earth can barely preserve. Our planet has repeatedly recycled its crust through plate tectonics, erosion, volcanism, impacts, and biological activity. Venus and Mars have also undergone extensive resurfacing. Mercury retains ancient terrain, yet even its history includes enormous impacts and volcanism. The distant outer solar system offers different archives. Charon's oldest landscapes have endured for billions of years, with comparatively little later modification. When we examine those terrains, we are looking at material shaped closer to the age of planetary formation itself. Binary systems strengthen that connection. A substantial fraction of large Kuiper Belt objects possess companions, although estimates depend on population and detection limits. Their existence shows that paired worlds are a natural outcome of outer solar system formation. Some binaries arose through collisions. Others may have formed through gravitational capture or gentle assembly. Pluto and Charon remain extraordinary because their particular encounter produced two substantial survivors. The collision had suitable energy, geometry, and angular momentum to create a bound system rather than complete merger or dispersal. Both bodies then evolved enough internally to preserve geological consequences of their beginnings. So, Charon connects two moments separated by almost the entire history of the solar system. A collision billions of years ago created the world. Then, in 1978, James Christie recognized its presence from a tiny distortion in Pluto's image. Ancient celestial mechanics and recent human curiosity became parts of the same history, permanently joined by our decision to look. A world without fractures would tell us far less. On Charon, nearly every feature carrying deep history exists because something once yielded. Its geology is readable precisely where matter failed, shifted, separated, flowed, or changed into something new. The first rupture came with Charon's creation. A primordial collision tore material from the bodies involved and rearranged it under gravity. Much later, freezing water expanded inside Charon, forcing its outer shell apart. Material from below found pathways through weakened crust. At the poles, radiation broke molecular bonds and allowed atoms to recombine into increasingly complex organic compounds. Breaking became a form of construction. The same pattern appears throughout nature. Stars emerge when enormous clouds of gas collapse under gravity. Inside them, nuclear fusion rearranges atomic nuclei, releasing energy while building heavier elements. Massive stars eventually die, and some explode as supernovae, scattering newly forged elements through space. Later generations of planets inherit that debris. We see smaller versions written across moons. Serenity Chasma is one such record. Its immense walls trace where Charon's crust separated under stresses generated from within. Nothing arranged those cliffs for appearance. Their geometry follows physical forces acting across geological time. What you see is an event preserved in water ice. Around Uranus, Miranda carries an even stranger landscape. Verona Rupus rises roughly 12 miles from top to bottom, making it among the greatest known cliffs in the solar system. Miranda's patchwork terrain may record major disruption and internal resurfacing, although the idea that the moon was completely shattered and reassembled remains uncertain. Its surface still carries evidence of extraordinary deformation. Enceladus records stress differently. Near its south pole, long parallel fractures called tiger stripes open pathways from a subsurface ocean. Water vapor, ice grains, salts, and organic material escape through them into space. The fractures expose an interior otherwise hidden beneath miles of ice. Europa offers another variation. Its surface is crossed by lineae, long bands and fractures shaped by repeated tidal stresses from Jupiter. The crust bends as Europa travels through its slightly elliptical orbit. Over time, those forces fracture and rearrange the icy exterior. Across these worlds, damage becomes evidence. A crack can reveal expansion. A cliff records displacement. A vent exposes buried water. A stain preserves chemistry. Matter retains consequences long after the forces responsible have disappeared. For almost 4 billion years, Charon carried such records without an observer nearby to interpret them. Its fractures remained, polar material accumulated. Pluto and Charon continued circling their shared center, completing orbit after orbit, while their history stayed physically present and unread. Then came an interval, almost too small to place on Charon's timeline. In 2015, New Horizons crossed the Pluto system. For the first time, something built by minds reached Charon closely enough to read what the broken ice had been preserving. $720 million is a small number beside 4 billion years. Yet that was approximately what humanity spent to reach Pluto and Charon, including development, launch, and operations through the historic flyby. Spread across the American population during those years, the cost amounted to roughly 80 cents per person. Even that investment almost never happened. Scientists had been developing serious Pluto mission concepts since the late 1980s and 1990s. Proposals competed against other destinations for limited planetary science funding. Designs changed, budgets tightened, programs disappeared and returned. New Horizons itself survived repeated threats before receiving approval and moving toward construction. Alan Stern, the mission's principal investigator, spent more than a decade pushing the project through that uncertainty. His work involved scientific arguments, engineering compromises, proposal revisions, funding battles, and congressional scrutiny. Thousands of other people eventually joined the effort. Only in January 2006 did their spacecraft finally leave Earth. By then, the idea was already old. Some researchers who helped establish the case for exploring Pluto decades earlier had retired before the encounter. Others had moved into different work. Some never lived to see the images arrive. Deep space exploration can exceed individual careers, forcing science to operate across generations. You can design an instrument today whose greatest measurement arrives decades later. Someone still in school may eventually interpret it. That pattern continued after New Horizons reached Pluto and Charon in July 2015. The spacecraft gathered its encounter observations rapidly, but transmitting everything home required roughly 16 months. From billions of miles away, information returned through an extremely limited radio connection. Analysis lasted much longer. Researchers are still extracting scientific value from those measurements more than a decade after the encounter. 24 hours near Pluto and Charon generated questions capable of supporting years of investigation, revised models, geological mapping, and competing interpretations. So what did $720 million and roughly 25 years of collective effort purchase? It gave us Charon's enormous canyon system. It revealed the reddish polar material, broad resurfaced plains, fractured terrain, and evidence consistent with profound internal evolution. A world that had existed beyond human perception for roughly 4 billion years suddenly possessed mapped landscapes and a reconstructible history. None of that knowledge changed Charon itself. Measuring Serenity Chasma does nothing to its walls. Reconstructing a vanished ocean cannot restore the water beneath the crust. Naming Mordor Macula does not alter a single molecule within its reddish material. Charon continues around Pluto exactly as physical law requires, indifferent to whether anyone understands its history. The change happened here. Matter crossed billions of miles as radio waves. Instruments became measurements. Measurements became evidence. Evidence became understanding inside human minds. For $720 million, humanity purchased no territory and extracted no resource. We acquired something less tangible. A previously unreadable world became knowable. Imagine placing one boot at the rim of Serenity Chasma. Beneath you, the ground ends almost vertically. The canyon descends roughly 3 to 4 miles, while its opposite wall lies perhaps 25 to 30 miles away. Yet this immense fracture crosses a moon only about 750 miles wide. Gravity changes everything here. Charon pulls downward with less than 3% of Earth's surface gravity. Drop a stone over the rim, and its descent would unfold slowly. Ignoring irregularities in the cliff, the fall could last more than 3 minutes before the stone reached the depths below. Even the horizon behaves differently. Because Charon is so small, its surface curves away much faster than Earth's. You would sense that curvature through distance itself. Features disappear beyond the horizon, surprisingly nearby, reminding you that this canyon occupies a significant fraction of an entire world. Above, there is no atmosphere producing a blue sky. Sunlight would illuminate the terrain while the surrounding sky remained black. Stars could remain visible whenever glare from the surface and sun allowed your eyes to detect them. There is no atmospheric scattering, no weather, and no airborne haze softening distant edges. Turn toward Pluto, and another unfamiliar geometry appears. Charon always presents the same hemisphere toward Pluto, while Pluto does the same toward Charon. From the Pluto-facing side, the larger world therefore remains fixed in approximately the same region of your sky. It never follows the familiar rhythm of rising and setting. Pluto would dominate the view. From roughly 12,000 miles away, its disk would appear several degrees across, vastly broader than Earth's moon appears from Earth. Bright Tombaugh, Reggio, and darker surrounding terrain could create visible contrasts across that enormous suspended globe. At your feet, water ice behaves more like rock. Surface temperatures can fall near minus 380 degrees Fahrenheit. Under such conditions, exposed ice is rigid, enduring, and extraordinarily resistant to ordinary change. There is no air to carry your footsteps. No wind crosses the canyon. A falling rock would produce no airborne sound for you to hear, even when it finally struck below. Only vibrations traveling through solid material could transmit the impact. A footprint pressed into loose surface material might survive for immense spans of time. With no rain, flowing water, vegetation, or ordinary weathering, change comes mainly through impacts, radiation, and extremely slow surface processes. And below your feet lies the reason Serenity Chasma exists. This gulf was opened as Charon's interior evolved and its water ice expanded during freezing, placing enormous stress upon the outer shell. The ocean vanished billions of years ago. Its fracture remained. Everything surrounding you in this scene comes from physical measurements and geological interpretation. The dimensions, gravity, temperature, orbital geometry, and ancient terrain were revealed through instruments carried across billions of miles by New Horizons, a spacecraft smaller than a car. For nearly 4 billion years, Charon had no name. No telescope recorded it. No observer measured its orbit. No catalog contained a place for it. The moon circled Pluto through an immense span of cosmic history, physically present yet absent from every known description of the universe. Around it, the solar system continued evolving. Worlds accumulated craters, orbits shifted, comets crossed enormous distances, nearby stars formed, aged, and disappeared. Through those changes, Pluto and Charon continued their mutual orbit, completing one revolution every 6.4 Earth days. Human beings arrived extraordinarily late. Our species has existed for roughly 300,000 years. Across almost all that time, generations watched the night sky without knowing Pluto existed. Even after telescopes appeared, the distant system remained unresolved. Charon's fractured landscapes, reddish polar material, and immense canyons occupied real space without entering human knowledge. That changed on June 22nd, 1978. Astronomer James Christie was examining photographic plates of Pluto at the United States Naval Observatory. He noticed an unusual elongation beside Pluto's image. Earlier photographs showed the same distortion appearing repeatedly, changing position according to a regular pattern. The apparent flaw was orbital evidence. Christie and astronomer Robert Harrington calculated that a companion body could explain the recurring bulge. Charon entered human knowledge first as an asymmetry in photographic light, supported by mathematics. Nobody had seen mountains, plains, or fractures. The object existed for us initially as motion and inference. Another 37 years passed before that changed. During July 2015, New Horizons crossed the Pluto system and returned images resolving Charon into an actual landscape. Scientists could finally examine terrain that earlier telescopes had compressed into a handful of pixels. As additional observations arrived, canyons acquired dimensions, plains revealed textures, and the polar region showed its distinctive coloration. Consider the sequence itself. Billions of years passed without a recorded observation. Then came a photographic irregularity. Mathematics turned that irregularity into a moon. Engineering transformed the moon into a destination. Instruments transformed the destination into measurements. We never needed to stand there. Human beings learned Charon's dimensions, composition, gravity, orbital behavior, surface geology, and probable internal history from billions of miles away. That knowledge depended upon equations predicting its motion, detectors separating wavelengths of light, and navigation precise enough to place a spacecraft beside a moving world after 9 years in flight. Science allows an unusual kind of contact. Matter can remain unreachable while becoming measurable. Distance can remain enormous while uncertainty becomes smaller. Charon itself experienced no transformation when James Christie recognized it. Nothing changed when New Horizons photographed its surface. Its orbit continued. Its ancient fractures remained where they had always been. The alteration occurred within the universe that could know itself. A place once absent from consciousness became measured, mapped, and understood. And when the details finally emerged, Charon was far richer than the distant blur had ever suggested. From Charon, the entire human story disappears into sunlight. Earth lies roughly 3 billion miles away, depending on where both worlds occupy their orbits. Even with perfect eyesight, you could not separate our planet as a recognizable world. It would be an exceedingly faint point, buried near the overwhelming brilliance of the Sunday. The sun itself would look unfamiliar. Its apparent width would be far too small for human eyes to resolve as the broad disk we see from Earth. Instead, you would perceive an intensely brilliant point, still brighter than anything else in Charon's sky. Its influence remains measurable even there. Solar radiation drives chemistry in Pluto's upper atmosphere and helps transform material transported toward Charon. Ultraviolet light participates in reactions that eventually contribute to the reddish compounds concentrated around Charon's North Pole. Yet Earth remains effectively absent from the view. Every human language developed there. Every city was built there. All recorded wars, discoveries, paintings, songs, machines, migrations, celebrations, and ordinary lives unfolded upon that unresolved speck. Every person you have ever known belongs to the same invisible point. Voyager 1 offered a related perspective in 1990. From roughly 3.7 billion miles away, the spacecraft photographed Earth as the famous pale blue dot. Our planet occupied less than a single pixel, suspended within scattered sunlight. From Charon, the geometry would be different, but the lesson in scale remains physical rather than symbolic. Earth possesses no special visibility simply because it matters enormously to us. Scale does not diminish significance, it establishes proportion. Charon never registered the arrival of New Horizons as anything resembling an event in its geological history. Serenity Chasma retained its shape. Polar chemistry continued. Pluto and Charon remained gravitationally locked together, completing the same orbital cycle they had followed long before humans existed. But something unusual had crossed the intervening space. We built a machine capable of surviving a journey lasting more than 9 years. Navigators directed it toward a moving target billions of miles away. Instruments gathered photons reflected from ancient terrain. Radio transmitters returned those measurements to Earth, where people reconstructed a landscape no human could physically approach. That accomplishment does not make humanity large beside the solar system. It reveals something different about scale. A species confined to one small planet learned to measure another world across billions of miles. We looked carefully enough to distinguish plains from highlands, identify surface compounds, calculate orbital motions, and reconstruct events billions of years older than ourselves. The measurements remained accountable to evidence. Where knowledge ended, uncertainty remained. Perhaps that is the perspective Charon leaves open. A universe can contain distances that make Earth effectively invisible, timescales that reduce human history to an instant, and worlds that never know we exist. And still, from that invisible Earth, something learned to look outward and ask what was there. Long before it became the name of a moon, Charon belonged to a river. In Greek mythology, the ferryman Charon carried the dead across the boundary into the underworld. His vessel moved between realms, joining a familiar shore to one beyond ordinary human experience. The astronomical name carries an unusually personal second history. After discovering Pluto's companion in 1978, James Christie proposed Charon. The opening letters echoed Char, a nickname for his wife, Charlene. Only afterward did the mythological association become part of the name's wider resonance. A private affection had found its way onto a world billions of miles from home. That mixture of myth and human storytelling continues across Charon's map. Serenity Chasma takes its name from the spacecraft Serenity in the television series Firefly. Ozterra recalls the imagined land created by Lyman Frank Baum. Vulcan Planitia honors the fictional planet Vulcan from Star Trek. These names were formally drawn from themes involving exploration, fictional destinations, and vessels of discovery. We use familiar stories to organize unfamiliar ground. Naming does something subtle to distance. A canyon identified only by coordinates remains measurable, yet difficult to hold in memory. Give it a name, and conversation becomes possible. Scientists can compare observations, publish maps, debate origins, and return mentally to the same feature without ever standing beside it. Charon itself occupies an appropriate place for such language. Pluto travels through the Kuiper Belt, a vast population of icy bodies beyond Neptune. Only a tiny fraction of that region has ever been examined closely by spacecraft. Beyond the Pluto system lie countless objects known mainly as points of light, orbital solutions, colors, and estimated sizes. In that sense, the ferryman remains near a boundary. On one side lies a solar system whose major planets have received orbiters, landers, rovers, atmospheric probes, or repeated flybys. Farther outward, direct exploration becomes sparse. New Horizons crossed that divide and spent only hours gathering its closest observations of Pluto and Charon before continuing deeper into the Kuiper Belt. What returned was stranger than the old telescopic blur suggested. Charon carried immense fractures, resurfaced plains, a reddish polar region, and evidence that its interior had once behaved very differently. The mythology supplied a name. Measurement supplied the world behind it. Names themselves can survive their makers. Ancient constellations still carry words inherited across thousands of years. Charon may similarly retain its name long after the circumstances of 1978 have faded from common memory. Future observers could speak it without knowing Charlene Christie ever lived. For now, we still know that small origin story. A husband placed four familiar letters into a proposed name. Scientists attached other human stories to newly revealed terrain. Then a spacecraft crossed the threshold those names helped us describe. Charon remains there, circling Pluto at the explored edge of an enormous region. Much of its surface is still poorly known. Beyond it, the Kuiper Belt continues outward, carrying worlds whose maps have no names yet. A tree ring can preserve a drought centuries after rain returns. A healed bone can preserve the direction of an ancient force. On Charon, fractures preserve something far older, the physical consequences of an ocean that disappeared billions of years ago. Geologists read such traces through a principle called uniformitarianism. In simple terms, the present is the key to the past. Physical laws observed now are assumed to have operated throughout geological history. Understand how matter behaves today, and ancient structures become evidence rather than decoration. Charon offers an unusually clear example. Its Great Canyon system records expansion within the moon as interior water froze. The smoother plains preserve the aftermath of material reaching and resurfacing parts of the exterior. At the northern pole, reddish tholins preserve another process, built as methane, originating from Pluto, was trapped, altered by radiation, and accumulated across immense spans of time. None of these records required an author. No intention placed them there. Water changed phase, ice responded to stress, molecules absorbed radiation, and gravity continued shaping the system. Physics and chemistry wrote the history simply by operating, yet we can read it. That ability rests upon something fundamental about nature. The physical behavior governing ice on Charon belongs to the same universe as ice inside a frozen pipe on Earth. Organic chemistry occurring under radiation at Charon's pole follows the same underlying rules studied in terrestrial laboratories. Distance changes conditions. It does not create another set of physical laws. Without that consistency, reconstruction would collapse. An observed fracture could tell us nothing reliable about ancient stress. A chemical signature would carry no dependable connection to the reactions that produced it. Instead, experiments performed here can help interpret a moon billions of miles away. Equations tested near Earth remain useful around Pluto. The universe appears consistent enough to be investigated across both distance and time. That gives Charon's broken terrain a different scientific meaning. Its fractures are neither failures nor tragedies. They are surviving consequences of geological change. A once warmer interior evolved, expanded, fractured its shell, resurfaced portions of the exterior, and eventually lost the energy needed to continue. What remains is evidence embedded directly in the landscape. For creatures whose senses evolved within one small environment, extracting that history required instruments, mathematics, laboratory chemistry, computer models, and years of argument. We gathered measurements, compared explanations, rejected weaker possibilities, and built interpretations that could survive contact with the data. That is our response to a readable universe. We examine what remains, then ask what sequence of real events could have produced it. Serenity Chasma had already existed for billions of years before complex life appeared on Earth. Human beings have known its form for only about a decade. The canyon belongs to deep geological time. Our understanding belongs to an instant. Both facts occupy the same universe, governed by the same laws. Charon has no awareness of its fractures. It does not recognize the ancient ocean that opened them, the material gathered at its pole, or the gravitational lock binding it to Pluto. These are meanings we supply through observation. The moon simply follows physics, as it has for roughly 4 billion years. Everything we call Charon's story exists within understanding. Canyon, ocean, chemistry, orbit, impact, all become a story only when evidence is measured and connected. As far as we know, we are the only place where the existence of Charon becomes knowledge. Carl Sagan described humanity as a way for the cosmos to know itself. Charon gives that idea a remarkably specific form. For almost its entire existence, this moon had no known observer. Then creatures made from the same cosmic material learned its diameter, mapped its terrain, reconstructed its interior, and traced events older than life on Earth. Even the substances involved carry deeper histories. Hydrogen within Charon's water formed during the first minutes after the Big Bang, roughly 13.8 billion years ago. Oxygen was manufactured inside earlier generations of stars and released before our solar system existed. Carbon incorporated into the molecules that eventually became tholins came through stellar nucleosynthesis, the creation of heavier elements inside stars. Radioactive elements within Charon's rocky interior supplied heat that helped sustain its ancient ocean. Some of the heaviest such elements were forged in extreme cosmic events long before the sun ignited. So Charon belongs to no separate chapter. It is cosmic history concentrated into one small world. Ancient matter gathered around a young star, collided, differentiated, warmed, froze, fractured, and endured. Those processes produced a landscape that could eventually be read. We belong to that history too. People built the telescopes that revealed Charon. Others proposed a journey there, defended its funding, assembled new horizons, programmed its encounter, and waited 16 months while its stored observations crossed billions of miles home. Scientists turned those signals into measurements, models, disagreements, revisions, and papers. Years later, you can lie awake while those discoveries become a story carried through a human voice. No additional meaning needs to be placed over the facts. Charon was fractured by ordinary physical laws operating under extraordinary conditions. Its greatest scars are roughly 4 billion years old. Our detailed knowledge of them is only about a decade old. Between those spans lies nearly the entire history of the moon, unread by us. Then, within one brief human generation, instruments reached it and the record became intelligible. Something ancient entered human knowledge for the first time. The ferryman named by mythology has crossed the outer darkness for ages, carrying an ancient record in ice and stone. Humanity arrived at that distant bank only recently. For now, this is enough. We looked carefully, across billions of miles, and what we found was real.